Chapter 7, The Quantum Mechanical Atom. This would be Chemistry of Molecular Nature by Hyssop. Alright, so chapter in context, we're going to describe light as a particle and a wave. We're going to look at some equations that relate energy to wavelength to frequency, and of course we'll discuss the wave-particle nature of light. We'll relate the line spectrum of hydrogen to energy levels of electrons. So it means we're going to be examining the Bohr model of hydrogen. We'll look at the wave mechanical models of atoms, and we'll define and use quantum numbers. In this chapter, we're also going to be able to write the ground state of electron configurations of atoms. Of course, most of you might be able to do that already. We'll connect the organization of the periodic table to electron configurations. That might be something you can do already. We'll look at the shapes of s, p, and d orbitals. Again, you might have seen that already as well. And last but not least, we'll look at electron configurations and the organization of the periodic table in order to predict chemical properties of elements. In other words, their charges, the octet rule, things of that nature. All right, so we're going to start off with electromagnetic energy, which of course means we're talking about electromagnetic radiation. In other words, we're looking at light as energy or waves, right? So we know that it can travel through space at the speed of light in a vacuum. So that's the constant c, and that's 2.9979 times 10 to the 8th meters per second. A lot of times we'll use 3, so 3.00 times 10 to the 8th. Successive series of these waves, or referred to as oscillations. So what are those? Well, that's the fluctuations in intensities of electrical and magnetic forces. And of course, this can vary regularly with time. And of course, we can get a wide range of energy from waves. So, properties of waves, the pieces we look at. The first thing I'm going to introduce you to would be the wavelength, and that's going to be lambda. Lambda is the distance between two successive peaks or troughs. Our units are going to be in meters, centimeters, nanometers, kilometers, some sort of meter, typically. Frequency, which is the Greek nu. This is the number of waves per second that pass a given point in space. Okay? Our units here will be hertz. Now, of course, a hertz is a cycle per second or per second. Okay, so you can think of it as per second or cycles per second. Our equation would be C is equal to lambda nu, or lambda times nu is equal to C. So our wavelength times our frequency will be a constant, which means they are inversely related, right? As one goes up, the other must go down. All right. The other thing we'll look at is amplitude. Amplitude is the maximum and the minimum height. So if I'm measuring from our line of origin, the maximum peak height would be the amplitude. Okay, that would be the intensity of the wave or how bright it is. All right, you guys are probably more familiar with amps than I am, to be quite honest. Varies with time as travels through space. Now we also have nodes. This is the points of zero amplitude. This is where the wave crosses through the axis and has a value of 0. The distance between your nodes will also remain constant. So if we're looking at a wave, we can see we have lambda being measured from peak to peak here. The amplitude is being measured from our line of origin. Whoops. Our line of origin up to the top of the peak. And of course, this is looking at distance. So that's why we're going to have wavelength. Here are our nodes being pointed out. So it's when that wave crosses over the point of origin or when it comes back across. Okay. All right. So the bright red color in fireworks is due to emission of light when strontium nitrate is heated. If the wavelength is 650 nanometers, what is the frequency of this light? So remember, C is going to be equal to lambda nu. So now if I have the wavelength, I can now calculate the frequency, right? So frequency then would be equal to C divided by lambda. At this point, we'd be able to plug and chuck. And so nu is equal to C over lambda. We're going to use 3.00, told you that gets commonly done there, times 10 to the 8th meters per second. We'll divide that by the wavelength given to us, which is 650 nanometers is 10 to the negative 9 meters. At this point, our meters will cancel out. We run that through our calculator and we'll get 4.6 times 10 to the 14 hertz, or cycles per second or per second. All right, WCBS broadcasts at a frequency of 880 kilohertz. What is the wavelength of their signal? So again, now we're going to be looking for the wavelength. So C is equal to lambda nu. All right, I'll give you a chance to pause here. And if you've tried the problem and you've unpaused, your answer should be 341 meters. And the way we get that is here. So we're going to have lambda is equal to C over nu. So we're going to take that 3.00 times 10 to the 8th, and we're going to divide it by 880, but it's kilohertz, right? So it's going to be 10 to the 3 hertz. And then we're going to run that through our calculator. We see the seconds cancels out, and that gives us 341 meters. All right. So once we start doing all these wavelengths and frequencies, and we're talking about the electromagnetic components, eventually we have to talk about the spectrum itself. So the spectrum is the entire thing. When we say the electromagnetic spectrum, that means we're going to be talking about all of the frequencies of light. So even the light we cannot see. Now, you don't need to worry about numbers here. Like as far as red light has a wavelength and it has a frequency. I don't expect you to know those numbers. However, I do want you to know the regions that it's broken into. So over here, when we start with high energy, short wavelengths, you can see we have gamma rays, then we turn into X-rays, then it goes ultraviolet, then visible, so that's that little tiny bit that we can see. You also need to know that the blue light is higher in energy than the red light. Okay? Then we have our infrared, then micro, and then finally radio waves and television waves. Okay? So our cell phones are operating down here, which makes sense. We want those to be low energy, right? So they're going to be real long wavelengths with low energy. All right, if we take that visible light and we pass it through a spectrum, right, through a prism, we can see the color spectrum. It's understood that it runs from about 400 to 700 nanometers. It's not always going to be true. Some get past a little bit of the blue here, but this is going to be our 400 nanometers down here. 700 nanometers up here is where it starts to become a red light, like a warming light used in like a cafeteria, if we have those anymore. This is obviously going to take the spectrum of all of our colors. So we're going to start with white light and we're going to pass it through. So we'll see a combination of all the other colors. So again, we can separate white light into the colors using a prism. Right? Now, again, what I'm going to ask you to do is be able to order things. So you want to pay attention to 3 topics. Here you can see list the following in order of increasing frequency, right? So you need to understand the wavelength. You need to understand the frequency. And you'll need to understand those relationships in accordance with energy. So if we say increasing frequency, that would be decreasing wavelength, but increasing energy, right? So energy and frequency are directly related or proportionally related. Wavelength and energy and wavelength and frequency are going to be in, oh my gosh, as one goes up, the other goes down. I lost that term. Oh my gosh, it's gone. Inversely, there it is, inversely related. All right. So if I was going to put these in order then, which one would be low energy, which one would be high energy? And then we want to put it in that order as going from low to high. So first we'd be looking for the lowest energy. So we know A and B are out, right? Because we want to be low energy. These are both high energy. So we know we're going to start with radio waves. Then what comes next? Microwaves or X-rays? And of course, if you think about the order, one direction or the other, remember we went radio, then next was micro, then it would be orange, then it would be blue, then it would be ultraviolet, but we don't have that one in this mix, then it would be X, and then it would be gamma. And so that means our answer then will be D. And again, you don't need to know the numbers for the cutoffs, but I do want you to know the order of which they come in. Now, when we start to talk about the atom in terms of waves and particles and all this stuff, what we like to do in most chemistry classes is take a tour through history. So we're going to start in the late 1800s. Now, the thinking in the late 1800s was that matter and energy were not related at all. They were distant from each other, right? They're very distinct items, and they didn't really go together, right? So it was thought that matter, you're made up of particles, and we can see the little pieces, and we can combine the little pieces. Energy was thought of as being waves. Okay? Now, once we get into the early 1900s, experiments start popping up that are going to show some not so good things with this idea, that they're not actually distinct at all, that there is some relationships. And so what they started having was they started doing experiments around electrons. Now remember, in the 1900s, electrons were a new thing, right? So the late 1800s, we had the cathode ray tube, and then we started to see that there was actually a charge to light, and that's probably what sparked a lot of interest at that point. And so once they saw there was charge to light, then that meant we had to start diving deeper in. And so a whole bunch of different experiments are going to come out, and we're going to start looking at a few of them. But these tiny charged particles are in some experiments, right? So the electrons are acting like tiny little charged particles, which we expect, and then they're acting like waves in other experiments. And of course, that's going to lead to the particle-wave duality. So let's talk first about the particle theory of light. Now, Max Planck and Albert Einstein, so the year is about 1905, they said electromagnetic radiation is like a stream of small packets of energy, right? So they're trying to make sense out of quantum mechanics, basically, calculus at the very beginning here. The quanta of energy, or it was coined as a photon. So Albert Einstein coined this quanta of energy as a photon. And so each photon is going to travel just like light. So it's going to move at the speed of light. Okay, so that means that a photon then has a frequency because it's a wave. Now, energy of a photon of electromagnetic radiation, of course, has to be proportional to its frequency. All right, and so here's where Max Planck added in, and he said, hey, energy is equal to this constant times nu, the frequency. Okay, and of course that constant, he ends up getting named after him, so it's called Planck's constant, the letter H, and it has a value of 6.626 times 10 to the negative 34 joules seconds. All right, so now we want to be able to use this in a math equation as well. So what is the frequency in seconds, per seconds, of radiation which has an energy of 3.371 times 10 to the negative 19 joules per photon? Now remember, E is equal to h nu. So now we're being asked what is the frequency. So now we want to know what is the energy divided by Planck's constant. So we're going to plug that in. We get 3.371 times 10 to the negative 19. We're going to divide that by 6.626. The joules, of course, will cancel out. We'll be left with per second, which is a frequency, so that's good news. We run that through our calculator, and we get 5.087 times 10 to the 14th. So remember, we have negative 19 plus 34, if you want to do it that way. All right, a microwave oven uses radiation with a frequency of 2,450 megahertz to warm up our food. What is the energy of such photons in joules? So what is the energy of the photon? There are options. I'll give you a moment here to pause, maybe work out the problem. All right, now if you've just pressed play, here is your answer. It is 1.62 times 10 to the negative 24. And how did we get there? We took E is equal to h nu, which means we plug and chug. We have 6.626 times 10 to the negative 34. And then we have 2,450 megahertz. And of course, mega is going to be 10 to the 6th. So at this point, our seconds will cancel out. Megahertz will cancel out. And we're left with 1.62 times 10 to the negative 24 joules. All right. So earlier we saw that the bright red color in fireworks is due to emission of 650 nanometers of light. when strontium nitrate is heated. What is the energy of a photon with this wavelength? And then what is the energy of a mole of photons with this wavelength? So first thing we'll do is we'll calculate energy. What is the energy of the mole? So we'll say E is equal to H nu. Now here, nanometers, that's not going to be a frequency. No, that's a wavelength. So we have to remember that C then is going to be equal to lambda nu. So now we're going to rearrange C equals lambda nu to solve for nu, and then we can plug it into this equation, which means we can say that E is going to be equal to H times C over lambda. Okay, so that's how we can plug in for the wavelength. Or if you prefer, you could use this equation first, get an answer, and then plug it in for nu and get the answer over there. Now, once you have the first answer, which will be either 3.1, 4.3, 3.1, 4.3, 3.1. So that's going to be one of those five. Then what we're going to do is we're going to multiply that by Avogadro's number, and that's how we're going to get the mole. So photons per mole, we can treat photons like a particle, and remember Avogadro's number is particles per mole. And so we can then multiply by Avogadro's number, and that'll give us the second number. All right, so I'm going to pause here. You've got some hints about how to solve this problem, and let's see how you do. All right, so hopefully you've worked out the problem on your own, and you came up with 3.1 times 10 to the negative 19. You multiplied that by Avogadro's number, and you got 1.8. If not, let's take a look at what you should have done. So the first thing we had was E equals H nu, but we were given a wavelength. So we converted that and used Hc over lambda. H, of course, is Planck's constant. C is the speed of light. We'll multiply those two together. Then we can divide by our wavelength that they gave us as 650 nanometers. That's 10 to the negative 9. Here we can see our seconds will cancel out with our per second. Our meters will cancel out. We'll be left with joules, which is a great unit for energy. So we have 3.1 times 10 to the negative 19. Now remember, that was for a single photon. Okay, that's a single photon. For a mole of photons, then what we're going to have to do is multiply by Avogadro's number, photons per mole. Photons will cancel out, and we'll have 1.8 times 10 to the 5th joules per mole. All right, so that's how we do that. Okay, so the next thing in history we're going to look at is the photoelectric effect. Okay, now this was a crazy effect. Here, we're going to shine light on a metal surface. Okay, now, if it's below a certain frequency, the light that is, nothing happens. The light just shines on the metal and whatever. Now, even with a very intense light, so if we crank up the amplitude, nothing happens. It just sits there. Now, once we get over a certain frequency, the number of electrons ejected increases as the intensity increases. So in other words, once I'm over a certain frequency and I start to crank up that amplitude, then we'll see the number of electrons ejected also cranks up. Okay? So the kinetic energy then of ejected electrons increases as the frequency increases. So the amount of energy the electrons are coming off with, that amount of energy actually goes up with the frequency. Now remember, there was nothing, and then all of a sudden it starts happening. Okay? So Ke then is equal to H nu minus Be. Okay, so the kinetic energy is equal to H nu minus Be. So H nu would be the energy of the light shining on the surface. Now Be, what is Be so weird? That's the binding energy of the electron. So Be is considered the binding electron. Excuse me, the binding energy of the electron. Now, what does this mean? Well, it means that energy is quantized, right? So remember those packets, those quanta? Well, it can only occur in discrete units of size, which is H nu. So one photon was one quantum of energy. So energy gained or lost has to be in whole number multiples of H nu. So now we can rearrange our equation a little bit and add to it. So E is equal to NH nu, where N is the number of moles of photons gained or lost. So that means that E then is equal to 6.02 times 10 to the 23rd h nu. So if light is required to start the reaction, then it must have light above a certain frequency for the reaction to get started. Below that minimum threshold energy, it doesn't matter how much intensity we have, it's not going to work. Okay? An example of this would be photosynthesis. So if you irradiate plants with infrared and microwave radiation, lower energy than visible light, then you get no photosynthesis. So a heat lamp doesn't help no matter how much intensity you turn on. The heat lamp will not help the plant start and complete photosynthesis. Now, if we take plants and we irradiate them with visible light, photosynthesis can occur. And if you turn that light up, you should get more intense photosynthesis as well. Okay, crazy but true. How much energy is contained in 1 mole of photons, each with the frequency 2.0 times 10 to the 13th? Now remember, E is going to be equal to 6.02 times 10 to the 23rd h nu. So I'm just going to plug and chug here. Okay, so we're going to take h, Planck's constant. We were given the frequency, we'll plug that in. We can see here that the joules will cancel out. Oh, excuse me, this should be moved over, right? The second will cancel out with the per second. Not that there's no joule over here, sorry about that. And that leaves us with joules per mole. Let's see, if a mole of photons has an energy of 1.60 times 10 to the negative 3 joules per mole, what is the frequency of each photon? Assume all photons have the same frequency. Again, we'll pause here for a second. And hopefully your answer is E, 4.01. Let's see how we would do this. We would say that the frequency is equal to E over Na times H, which is Avogadro's number. We're going to get rid of that mole. So we know our energy is in joules per mole. So we're going to take 1.6 times 10 to the negative 3. We're going to divide by per mole, right, times Planck's constant. So our joules will cancel out. Our moles will cancel out. We'll be left with per second. We'll run this through our calculator, and hopefully that's how we ended up with 4.01 times 10 to the 6th. All right, so we're about 22 minutes in, so we're going to call this a wrap for segment 1. And in the next segment, we're going to turn our attention to the electronic structure of the atom. Okay, and we're going to start walking our way through history still. So stay tuned for segment 2, electronic structure of the atom.